shall look at the effect of degree in polynomial regression on overfitting and underfitting. I shall start by explaining the problem statement and then walk you through a simple experiment in Python, which will help you visualize and understand the idea rather than simply looking at the mathematical aspect of polynomial regression. In this experiment, we shall use some simple temperature-like data and then try to fit polynomials of various degrees on the dataset. By the end of this video, we will understand underfitting, overfitting, and proper fitting. The key takeaway of this video will be whether increasing the polynomial degree always improves the model. Class notes discuss the day-wise mean temperature for Guwahati city from 1st January 2024 to 31st December 2024 as shown in figure 1. It can be observed that the plot is more or less a smooth curve with higher temperatures in summer and lower temperatures in winter. There is slight noise since it is real-world data, but the overall behavior of the model can be considered to be a smooth curve with one peak. Our aim is to use a similar dataset. For the purpose of this assignment, we generate synthetic data. We shall consider a smooth, non-linear signal and add small noise to it to make it more real-world-like. The reason behind using synthetic data is that synthetic data gives us a known ground truth. We know the exact mathematical function that generates the data. This allows us to clearly evaluate how well different polynomial models approximate the true underlying pattern. It also gives us a controlled environment where we can adjust noise and complexity to observe underfitting and overfitting more clearly. This makes the model behavior easier to visualize and interpret. For this experiment, I generated a dataset consisting of 60 data points. To properly evaluate model performance, I split the data into training and test sets, 70% for training and 30% for testing. The training data is used to fit the polynomial model, while the test data helps us evaluate how well the model generalizes to unseen data. I tested 3 representative degrees, a low degree of 2, a medium degree which corresponds to the optimal model based on test error, and a high degree of 15. We shall see that the low degree polynomial is too simple and cannot capture the underlying structure of the data. The medium degree polynomial provides a balanced fit and captures the true trend effectively. The high degree polynomial becomes overly flexible and starts fitting noise in the training data. Let me quickly walk you through the code. The code here is pretty simple. We start by importing the necessary libraries, which is NumPy and Matplotlib, and then we initialize the random seed and generate the noise. Here in this cell, we see 5 functions that can be used to generate the synthetic dataset. And then we plot the data. Once the data is generated, we split it in a 70:30 ratio for training and testing. This particular function here takes in the degree and fits a polynomial to the synthetic data and returns the train and test errors. Here, we fit the polynomials of degrees ranging from 1 to 15 and plot the error versus degree graph. This graph shows both the training error and testing error and how they vary over changing polynomial degree. In this particular cell, the required statements can be uncommented from this block to see the polynomial fit for the desired degrees, which can be seen in this graph here. Now let us proceed to see the results. Here is the data generated for the first model and the training and testing accuracy. Model 1 represents a smooth Gaussian-shaped peak centered around t is equal to 0.5 with added random noise. The underlying function is 25 plus 8 e power minus 30 into t minus half square plus a random noise. On the right, we observe the training and test error plotted against polynomial degree. As expected, the training error decreases steadily as the degree increases. However, the test error initially decreases, reaches a minimum of about degree is 8, and then starts increasing, clearly showing the onset of overfitting. This demonstrates that increasing model complexity beyond a certain point harms generalization performance. Now let us have a look at the polynomial fitting this data. When we try to fit a polynomial with degree 1, it is a straight line. But this polynomial starts to mimic the dataset as visible here with degree 2. Degree 8 had the least test error and here is the plot. We can see that it fits the data well and handles noise as well. But as we increase the degree to about 15, we can see that the polynomial starts becoming more wiggly and tries to fit in the noise. In these experiments, we can clearly observe the effect of polynomial degree on model behavior. For low degree polynomials, the model is too simple and cannot capture the true structure of the data. This results in underfitting. For medium degree polynomials, the model captures the underlying pattern effectively while maintaining a smooth and stable fit. This represents the optimal balance between bias and variance. For high degree polynomials, the model becomes very wiggly and starts following noise in the training data instead of the true signal. This leads to overfitting and poor generalization on test data. These observations clearly demonstrate that increasing complexity does not always improve model performance. For each degree, I computed the training mean squared error and the test mean square error. The training MSE measures how well the model fits the training data, while the test MSE evaluates how the model generalizes to unseen data. As expected, the training error decreases consistently as the polynomial degree increases. However, the test error initially decreases, reaches a minimum at an optimal degree, and then starts increasing. This U-shaped behavior of the test error clearly illustrates the transition from underfitting to overfitting. The key interpretation from the error curves is that the minimum test error indicates the optimal model complexity. This is the degree at which the model best balances bias and variance. Importantly, this optimal degree does not necessarily correspond to the highest polynomial degree. In fact, very high degree polynomials may achieve extremely low training error, but they often perform worse on test data. This clearly shows that increasing complexity beyond a certain point harms generalization. To conclude, increasing the polynomial degree always reduces training error. However, beyond a certain point, the test error increases due to overfitting. This shows that more complex models are not always better. The optimal model complexity is the one that minimizes test error. Therefore, polynomial regression requires careful degree selection to balance bias and variance. Thank you.